Alrighty then. Let's navigate on over to where we need to go and get this whole thing started here. Alrighty. Da-da-da. But for anyone just joining us, this is Universe at Home, as my screen is now lovely displaying. And what that means is this is just a nice public talk about things in astrophysics. And so today we're going to go over, I'm going to wait for people to kind of stabilize for a bit, and we'll introduce ourselves and we'll go over what kind of topics we're going to be talking about today. And that's going to be focusing on the early parts of the universe. And I mean, within the first even split second of the universe, however you want to define that, the actual beginning and what that means for how we live today. So, my name is Maxwell Kushel. I am an undergraduate here at the University of Minnesota, and I am studying right now, well, I'm studying astrophysics. I'm working with Professor Pat Kelly on a turbo project, which is a project on this small telescope that's going to be observing supernovae, among many other things, constantly watching the sky, trying to find some new information of what's out there. And then I'll let my colleagues here introduce themselves as well.
Hi, everybody. My name is Haley. I am a second-year graduate student here at the University of Minnesota in the astrophysics program. I also work with Professor Pat Kelly, but on a slightly different project. I am studying the environments around supernovae through the process of gravitational lensing, which is definitely not the topic of this talk, but if there's extra time at the end, I'd be happy to answer questions on those topics. And I will hand it off to Olivia.
Hi, I'm Olivia. I am a third-year undergraduate here at the University of Minnesota. I am studying astrophysics, physics, and German. And funnily enough, the topic that I'm going to be talking about today, the matter-antimatter asymmetry in the universe, is actually a presentation that I gave last week in German. So I'm giving it again. So that'll be interesting. I get to do it in English now.
All right, perfect. Well, without further ado, let's get started and talk about, well, what we have to talk about today. There we are. So the title of the topic is the first 20 minutes in 20 minutes. We're going to try to really condense this as much as possible. The entire topic, I want to preface it with saying that just about every sentence that we say here today is almost worth an entire book. That's not really saying anything highly of ourselves. It's really just saying highly of the science. And it's very complicated stuff, but I really do feel that with a quick explanation, people can understand why these things are so important and why they are so fascinating. And we think that that's really important for the general public to understand what astrophysicists do, not only because it's cool, but because it can lead to many changes in either society or, if you're not too interested in that, at least some sci-fi. So I'm going to be talking about a period in time called inflation. It's a proposed theory for the beginning of the Big Bang and helps explain some of the problems that the Big Bang has in terms of the mathematics. Now, in order to explain that, I do kind of have to go through the timeline of the Big Bang and refresh everyone's memory, because I'm assuming it's not as on top of your memory as it might be as on one of our colleagues' memory. So I'm going to start off with just an introduction on the Big Bang. Then we'll go into what's called the cosmic microwave background, this radiation that is coming from everywhere in the sky. We'll connect those two and talk about this thing called the horizon problem. We'll go into how inflation solves the horizon problem, but then creates new problems, such as the variations problem, which really can just be summed up with the fact that if the universe started in this big universal, or I'll use the term isotropic, which really just means same in every direction, it started out in this isotropic explosion, well then why is the universe, at least on our scale, very anisotropic, meaning there's a lot of variation. And there has to be a reason for that. If I'm going to tell you that we started in some universal or some even explosion. So we'll get into that. And then my colleague here, Olivia, will go into antimatter and talking about exactly what antimatter is, the exact problem of the matter-antimatter asymmetry, which you may hear called the baryonic asymmetry. Baryons are just what astrophysicists like to call everything other than dark matter. There is a technical definition, but it really just means the matter that makes up you, me, and everything around you is baryonic. So you might hear it called the baryonic asymmetry problem, or more commonly, the matter-antimatter problem. And she'll go through a couple solutions to that. So, all right, let's go into inflation. Let's go into the topic that I'm talking about today. And I have an image here for you just to help show exactly where in the universe we're talking about. And I mean where in time. Now, the right-hand side of this diagram can be thought of as exactly as the present. The left-hand side is the beginning of the universe in the Big Bang, and everything in between is everything in between. I am going to mainly be talking about that period on the far left labeled inflation. It's that period where we really go from such a tiny, minuscule point in this exponential increase to a much, much larger universe. And that period is introduced in theory to explain a lot of problems that arise from the Big Bang theory. And so this is just a conceptual view of what I'm talking about. And I find it very interesting to look at things like this because it reminds you that science is able to go into the earliest seconds of the universe. And that is truly something to be fascinated by. So let's go into the Big Bang then. I keep talking about it. Let's go into it and let's try to refresh our memories of what is the Big Bang. Well, the Big Bang is really just the theory that the universe started out in what's called a hot, dense state, meaning it was really small, its temperature was extraordinarily high, and that caused it to expand into the universe that we know today. Well, that general view, that beginner's view of the Big Bang assumes a thing called radiation domination, meaning that a majority of what was in the universe at that time was light. So a majority of the energy was just in the form of light. And you can kind of help conceptualize that by thinking of right now where you are at matter dominated. Now the universe right now is lambda dominated. If you want to know, we can go into that. But just to help conceptualize what I mean by radiation dominated, I mean light is the main thing around you. Well, this helps predict and is predicted by the cosmic microwave background. So in order to kind of talk about this, I'll touch back on the Big Bang in a little bit, but let's go into what the cosmic microwave background is, because we need to know that in order to know why do we even think the Big Bang occurred. So let's go into it. It's abbreviated as the CMB, and I'll probably be calling it that for the rest of my talk, and you'll mostly hear people call it the CMB. What that means is this universal radiation. As I said, a fancy term for it is isotropic, meaning that it's the same in all directions. And that's the key kicker there, is that it's the same in every direction, and it is seemingly constant. Now, if we zoom in on it, there's small variations, and that once again yields its own fun answers. But it's relatively uniform. And from a thermal point of view, looking at it as that kind of spectrum, it is uniform. So we have this universal radiation coming from all around us, and it deserves then the question, why is it so universal? So for a little history here, the cosmic microwave background was produced and released when the universe was close to 300,000 years old. And ever since that point in time, and for reference, right now, we're at about 13.7 billion years. So this was a long time ago, and it traveled all throughout that time, all throughout that space, and reaches us unimpeded. Well, it begs the question then, if this radiation is universal, then at about 300,000 years old, the universe must have been universal. And so we go into a problem called the horizon problem. And to help explain that, I have a fun little analogy for you. But what is the horizon problem? So I've just explained to you that we have this cosmic microwave background. That's fine and well. Radiation is coming from everywhere all the time. Neat. But there's a problem with that. Remember how I said the Big Bang was radiation dominated? Well, that mathematically determines how the universe expands. There's a problem there, though. So and to analyze that problem, let's think of the universe as an orchestra. So when the universe started, this orchestra is playing a song, and in order for it to play one song, something that is universal, the same, it has to see the conductor. That's the only rule we have here. Well, the universe is expanding and everything is going as planned, and we hit at about 300,000, and the conductor decides, you know what, we're going to hold this note. We're going to stop here. Well, in order for the rest of the orchestra to know that, they have to see the conductor. Well, how fast the conductor moves is determined by what the universe is made of. And if it's radiation, it turns out that no member of the orchestra can see the conductor. It actually turns out that the horizon that they have, that they can see, is as big as your thumb is on the sky. It's about 1 degree. It's ridiculously small compared to what it has to be. This is a massive discrepancy. Why? We have the song. We have the radiation consistently coming down day in and day night. If we have the radiation, they have to be able to see the conductor. We have to have something that is universal. Well, what explains this? Inflation explains this. So what is inflation? I've said the word for the past 10 minutes. Let's get into it. It's a period of time before the universe was 1 second old, where expansion was so rapid that a sphere of about 1 meter in size became the observable universe. The atomic scale was blown up to about the size of an elephant. What does this do then? Why would any scientist think of that? That seems outlandish. That seems crazy. Well, it turns out that mathematically it works, that if you have inflation, then the orchestra can see the conductor. Then the expansion works in a way where at 300,000 years, they're able to see what's going on, and they're able to play that last uniform note that we can now see today and predict things like this. So if you're interested in fancy scientific words, we call this orchestra analogy kind of the universe in causal contact. What I mean is, in order for it to have something homogeneously or isotropically, meaning everywhere universally, then it must be in causal contact, meaning the physics at one point communicate, if you will, with another point. So then we introduce another problem by solving that problem. That happens far too many times in physics. And well, you might wonder, well, what problem did we introduce? I haven't mentioned it yet. Well, the problem we introduced was I just went through a whole rant about how everything is universal. Now, at 300,000 years, it's perfectly isotropic, and it's this beautiful song. But look around you. The universe is not homogeneous, not on your scale. Don't get angry at me, cosmologists. I know it's homogeneous on that scale, but on your scale, on my scale, it is extraordinarily obviously not. I mean, the fact that you can hear me right now shows that it's not homogeneous. We have variation. We have planets and stars and galaxies and clusters and walls and voids and all of these fancy things in the universe. My whole field wouldn't exist if there wasn't variation. So how do we explain that? If I just told you that we introduced inflation to help explain how things are universal and in contact, why is it so inhomogeneous? Well, to explain that, I have another analogy for you. Why? Because revealing the math would require quite a few classes to explain. I know that. I'm in one right now. And I call it the Minnesotan field analogy. And I call it the Minnesotan field analogy because we need a relatively flat field. And that seems to be the case here. So let's imagine ourselves in a relatively flat field. We find a nice flat area. And I mean an area in about 1 meter in size. I realize I am at least giving this talk in the United States, so I need to give a little more relatable measurements. So imagine a refrigerator. We have a flat spot the size of 1 cylindrical refrigerator. Now, according to the mathematics, when we talk about inflation, we have this field of potential created by something we call the inflaton. And this field is kind of the primordial universe right before it expanded. And in order for the math to work out, for this field to then cause inflation, we need a point that is relatively flat. So we need your cylindrical refrigerator in your field. And at that point, the math works out. The shock wave happens and the universe expands, and we create this beautiful inflation that creates reality around you. But I said find a relatively flat spot. I didn't say clear off the spot. We all know if we go into a field, there's going to be rocks, there's going to be grass, there's going to be tiny things that on the scale of the field are flat, but zoomed in are large and massive distortions. Well, when we're talking about the actual physics, we're talking about the particles, those rocks and leaves and blades of grass are quantum oscillations. Fancy words for variations on that quantum scale. And it turns out that if the inflaton, this primordial particle that was required for inflation, if that on the quantum scale was oscillating, which you can reason that it was if you know anything about quantum, you can think, well, Heisenberg uncertainty principle or Schrodinger's cat, we got variation on the quantum scale. That's nothing new. Well, those quantum variations, I told you the atomic scale became about the size of an elephant. Those quantum oscillations became important, became large enough to possibly seed the oscillations that were necessary, the variations, using a lot of shun words, really to just say that these tiny things that changed created the massive changes around you in the universe. Well, if you have any questions about that, please write them in the chat. My colleague here, Haley, will continue to write them down for us, and we will address as many as we can right after the rest of the talk. But I should really pass it off to Olivia now. So I'm going to stop my screen sharing, and you can then see all of our beautiful faces, and I'll stop talking. Olivia, you can go ahead.
All right, just give me one moment.
While Olivia sets up, I'd just like to remind everybody that the chat is open for questions. It's best if you just type out your question the second it pops into your head, and then we'll just store them and answer as many as we can afterwards. But you can also definitely ask questions if you think of them after the talks as well.
Okay. So before I talk about the matter-antimatter asymmetry in the universe, I think it's important to explain what antimatter is first. So it's not sci-fi. The stuff actually is real, like black holes and all that stuff. So yeah. And so antimatter is nearly the exact same as matter. Like it has the same mass, same interaction with light. It like looks exactly the same, but the only difference is that they have the opposite electrical charge. And what this means is that when antimatter and matter make contact, both are annihilated. So that just means they're destroyed. And then, so like, we already know that like, you can't like destroy stuff and then have it like be gone forever. So like what happens when they're annihilated is that they release energy in the form of light. So this is what we see in this image right here. So this proton and antiproton come together at that point right in the middle. And then these two light waves come out, and this actually follows the famous equation that I think everybody knows, E equals mc squared. So the energy that is released in the form of light here is just the mass of both of these particles together times the speed of light squared. We know antimatter is real, not because we know it should be real in theory, but also because we have actually created it. But we haven't created a lot. We've created about a total of 20 nanograms, probably a lot less. So this has costed like millions of dollars, but we know it's real, so it's worth the cost. So one place where antimatter is made here is the antiproton decelerator in CERN in Switzerland. So what this machine does in basic is that it gets a lot of energy in one point, and then it, well, I should explain something else first. So I sort of skipped ahead. I told you that they can annihilate, but I need to tell you how we can make antimatter. So it's made by reversing the annihilation process. So you just get a bunch of energy in one spot, and then antimatter and matter pairs can be spontaneously created. So what this machine does is that it brings all this energy into one point. It creates some antimatter-matter particle pair, and then it slows down the antiparticles so that we can observe them. So this is more about the antimatter-matter pair creation. So what this the official name for it is called pair production. So like I said, you get all of this energy into one spot. In this example, we have some gamma ray photons. Gamma rays are the most energetic form of electromagnetic radiation. So it's a good source of light to make antimatter and matter. But the most important thing is what we have noticed from countless experiments is that when you do this, when you make matter and antimatter together, it is always the exact same amount. It's always the exact same amount, no matter what. And like I said before, both pair production and annihilation both follow the famous equation E equals mc squared. So we're not actually getting rid of anything, we're just transferring it from one form to the other. So like we already talked about, what Maxwell talked about, the Big Bang was this immensely energetic and hot and event. So and this is actually the perfect conditions for making matter and antimatter together if you have all this energy into one spot. So the Big Bang, all this energy is one spot, we make matter and antimatter. And from what we know, we think that there should be equal amounts of both. But we also know that when antimatter and matter are together, they like to annihilate each other. So the question is, why did everything not annihilate? And why do we only see matter in the observable universe, but no antimatter? That is sort of the big question. So one solution that we have is that the laws of physics during the Big Bang were in some way different. And these differences could have allowed for more matter rather than antimatter to be produced. So one prediction that we have is that for every 10 billion antimatter particles, that there were 1,000,001 matter particles, and that everything we see today is the leftover 1 in a billion, or 10 billion particles that were left over. And then another prediction is that back to what Maxwell already talked about, during inflation, we know that it was like extremely fast. And as we can see in this imagery, we have an extremely steep incline going from inflation, and then for the rest of the universe, it was really smooth. So what we think is that during this inflation period, the expansion might have been so fast that the particle and antiparticle pairs couldn't have annihilated each other. So if you have two particles together, the expansion was too fast. They were going faster than the antimatter and matter particles could have gone to annihilate each other. So what we think this could have resulted in is parts of the universe where it is matter dominated, like we see in the observable universe. We can look out into the sky, but there's also parts of the universe where it could be dominated by antimatter, which we can't see because the inflation was just too fast. And there are also other theories, but these sorry, this is the same theory I was talking about. What the problem with the theory I just talked about is that if there are parts of the universe that are dominated by matter or by antimatter, then we would be able to tell these apart from matter. So theoretically, we could have already looked at antimatter out in space, but we just don't know it's antimatter because it looks exactly the same. But if this were true, what we would expect to see is that there has to be at some point where it goes from matter to antimatter, and at those boundaries, we would have to see the matter and antimatter coming together and annihilating each other. So this is what's in this image right here. We have a galaxy made of matter and an anti-galaxy made of antimatter. And what we would see at these boundaries are these like huge like walls of light. And this is what is depicted right here called a gamma ray burst. So it's just them annihilating and releasing a bunch of light. That's what gamma rays are. So here's what I wanted to talk about. So there are actually more theories that explain the antimatter-matter asymmetry, but they can get really technical really fast, so I don't want to go too deep into them. But this other theory that I liked that I talked about in my German class was that the universe is actually symmetric in time. So what that means is that well, we're going forward, that's the positive time direction, and that there's also another side of the universe where the time direction is just negative. That doesn't mean it's going backwards. It's just in a different direction. So like you can walk forwards, and then you can also walk backwards. So what this means is that like there could be a other part of the universe where there's a time that like precedes but not really precedes, where it's actually dominated by antimatter. I guess that doesn't make too much sense, but I just wanted to mention it since that's the third most popular theory for this. But yeah, I think my part of the presentation's done.
Okay, great. Well, thank you to Max and Olivia for those talks. And we will now move into some fun questions that we have got in the chat so far. So we're going to start with a question from Roger, who asks a very big question, which is, what do theorists believe existed, if anything, before the Big Bang? And if the answer is nothing, then how can all of that matter and energy come from nothing at all?
Oof, that is a big one. Okay, I want to explain it in kind of a two-part. So first, I want to talk about what do we think, at least in terms of the theory I explained today, what do we think the early universe was? And then we can kind of talk about what started beforehand. So as I said, we kind of had this potential field, which is called the inflaton field, if you're looking for something Googleable. And all I said was we needed a place that was relatively flat. And that's not a huge constraint. And so you could imagine if one section of this field is flat, many sections of this field is flat. And so one of the theories is that the beginning, if you will, or that stuff before, is this field of potential. And we have this infinite inflation is the exact theory, infinite inflation, where each patch is inflating at different times. And that's what seeds the multiverse theory. So that's at least according one of the big, more fun ones for the theory I claimed. I'm not sure if my colleagues want to say anything else. I'm personally not qualified to talk about pre-Big Bang. I'm barely qualified to talk about Big Bang.
Well, I think the big main answer on this question, which is something that we get all the time, it's a very common question because it's a good question. The problem is it's a very difficult question to answer with the actual scientific tools that we have to study astronomy, because we literally cannot see anything that would have happened before the Big Bang. So it's really difficult to test theories on this, but there's, of course, lots of different, somewhat crazy theories that people come up with, like, you know, a universe that expands and then collapses back in on itself, or multiverses, or bubble universes that pop and cause the next Big Bang. But I think it's pretty safe to say that that is not a question that we will know the answer to in any real way in at least our lifetimes, and honestly, possibly ever, which I know is a really unsatisfying answer to that question, but is just kind of how it is, unfortunately. But I think with that, we'll move on to the next question, which is from Bob. And his question is, was the inflation faster than the speed of light?
Ooh, now that's a fun calculation.
think it was, wasn't it?
It should have been, yes.
Yes. I mean, the basic answer is yes. It just
Right,
depends on
yeah,
the scale you're looking at, basically.
Right. In terms of like a Mach speed, that is really the big debate, because how long inflation was depends on what you're defining as the inflaton. To give a short, sweet answer, way faster than the speed of light. We're talking about something that was within a fraction of a second. If you want a real number, you're going point to maybe 23, 20 zeros until you hit an actual number past that decimal. This is a very short period of time.
But the other, side of this question that comes up a lot, because I think people do hear that inflation was faster than the speed of light, is that sometimes people get confused because they've heard that it's physically impossible for anything to move faster than the speed of light. And that's still true. The idea, as we'll do a little bit of a demonstration on this, which will hopefully make it clearer a little bit later, but the idea is that nothing was actually moving faster than the speed of light during the period of inflation. It's just that this empty space itself was expanding faster than the speed of light. But that's not the same thing as throwing a ball faster than the speed of light, which is completely impossible.
I guess a good way to say it is that nothing can go faster than the speed of light, nothing being empty space itself.
Yes, that's a nice way, Olivia. Okay, the next question we have is from Ron, who asks, so prior to the expansion, when the bang itself occurred, what does the mathematics say to explain what actually caused or could have caused the event to happen? Like, what was the trigger for the Big Bang?
So I guess I would classify this as one of the unanswered questions of physics. We don't know exactly why it happened, but there are theories, but I don't think I'm qualified to talk about all of them. Do any of you have any idea?
That is a strange one, because one of the ways inflation is introduced is to help solve a constraint problem. If we take out inflation, we just assume the Big Bang blew up and just kind of universally expanded in a nicer fashion, then we come to a point where it has to be, the numbers turn out where the energy densities, which help us determine whether the universe is flat or curved, the energy densities have to be extraordinarily close to a specific value. So the reason why inflation is introduced is because that takes out that necessity of this high accuracy. So yeah, as Olivia was saying, it's one of the big unanswered questions. And one of the problems is some of the big theories now are really muddying the waters, if you will, for what could have actually started it. So it's a big question, and it's only getting bigger.
Yeah, I think that's pretty much all we can say about it. This is similar to our first question about what happened or existed before the Big Bang, which is that this is something that would be really difficult to ever be able to test. But you hear common things. There's a lot of very complicated mathematical descriptions. Like if you hear the word the singularity, that is a very strange, almost some people would say exotic, like mathematical form. And I'm not an advanced enough mathematician to explain all of that. But then you also hear a lot of, the word quantum gets thrown around a lot, but that honestly probably is the meat of it, is some sort of fluctuations in quantum fields, which again, I know is kind of an unsatisfying answer, but that is the nature of these kind of questions, unfortunately. Ron had another question about time. So Ron wants to know also, again, prior to the Big Bang event, since space didn't exist, then could it be that there was no time as well?
I want to give a satisfying answer. I really do. But time and space are intimately linked. And all theories that we've developed, and well, I suppose I shouldn't say all, there were theories pre-Einstein, but post-Einstein, theories are mainly developed under the idea that space and time are intimately connected and that you can't necessarily separate them. But that is an interesting question, and it leads into the idea of, do we create space as we expand, or do we expand into space that was already there? And I think that kind of ties into your question, because if we expand into space that is already there, then I would argue against that idea that we could have been either outside of time or outside of space. But if we create it, well, then the idea of us creating an addition onto space, that being time, well, why not? I mean, that's definitely nothing supported by current theory, but only because, yeah, time and space are intimately linked. And I like to give things that are Googleable. It's Minkowski's spacetime. The real heavy lifter was Noether. Shout out to that mathematician who figured out many fancy things. But yeah, that could very well be the case if we are creating space. But if we are moving into space, then I don't think that could explain it.
I think that question could be partially, well, your thing about are we moving into space that was already there, or are we creating space? That could be related to, and I know we didn't talk about this during the presentation, but dark energy, which I think people in the chat should look up because it's a really interesting topic. But dark energy is sort of the what's the best way to explain it? The energy of empty space itself. So I think if we could somehow figure out what dark energy is, because we actually don't know what it is, that could help answer that question. So it would be like, are we creating dark energy, or are we moving into dark energy that was already there?
All right, and we have one more question, which is on a completely different topic, but we are happy to answer pretty much anything. So the question is, from Peter, how can gamma rays be observed and measured? And I can answer this a little bit. I'm definitely not a gamma ray astronomer, because that is a whole field of work that people dedicate lots of time and energy to. But a quick bit of background: gamma rays are the highest energy form of light that exists in the universe. So if something has just extremely high energy, then we classify it as a gamma ray. And this was kind of bigger news in like the mid, I don't know, 80s-ish, 90s, of observations happening of gamma rays and scientists being unable to figure out where they came from. But they're also really difficult to detect because they're so rare. Just simply having light at that high of an energy is a really rare thing. So in order to detect gamma rays, you can't just do what we usually do in astronomy, which is point a telescope at a very small portion of the sky, because it's just so unlikely that you would actually observe a gamma ray in that tiny portion. So what gamma ray telescopes basically have to have is giant detectors so that they're able to look at a really wide area of the sky. And in order to make that physically feasible, they have to have really, what we would say, poor resolution compared to what we usually want for a standard telescope. And what that means is that a single pixel on the telescope would be the size of like a whole galaxy on the sky. And the point is that we don't need to be able to resolve the difference between points that are really close together, because we're probably not going to see a gamma ray anyway. But if we can see a large portion of the sky, then we might be able to observe and measure the energy of a gamma ray and know at least the general direction it's coming from. And then we could try to point higher resolution telescopes at the same area. But there are lots of gamma ray observatories on Earth and a couple in space, although one of them more famous ones in space did retire, but gamma rays still are somewhat of a mystery in astronomy because we definitely can't necessarily account for all of them, but some events that might cause gamma rays are things like supernovae and events that are even more, explosive than that, such as when two black holes collide with one another, but also things that you might not expect, like just radioactive decay in space of materials that we don't have a lot of, and therefore that's why it's so rare. And also another hypothesis is that part of it comes from the annihilation of matter and antimatter, that which Olivia talked about in her talk, that might still be happening occasionally today. We think of basically all of the antimatter being gone, but it's still pretty likely that given the size of the universe, there might be a few stray particles floating around, and they release very high energy when they collide. So that could be another source of gamma rays. I don't know if Maxwell or Olivia have anything to add to that.
I think that was a good explanation.
Okay, and we will move on then to another question. This one from Dick, who asks, why do we think that there is dark energy? It's a great question.
That's a super, super fun one. I think it's worth mentioning a quick history of dark energy because I think it's really kind of funny. So Einstein, going through his life, figuring out the universe and coming up with models of the universe, comes up with a model of the universe. And what it requires is this parameter he termed lambda. And it's this constant energy density, and meaning that it's, as Olivia had said, it's kind of the energy of emptiness. So if I create space, just empty space, kind of like a blank text document, well, that text document took energy to make. And that's kind of what this constant is. So I think it's worth mentioning that because Einstein hated it, absolutely abhorred it, thought it was one of the biggest mistakes in his career. And the community was super torn on it for a long time until more evidence which constrained the universe to most likely being flat required then this energy, this constant energy density. So what do I mean by that? Well, it turns out, and Haley had briefly mentioned supernovae. Turns out supernovae type 1a have a super, super well-known light curve, and they have a very, basically their actions are predictable. And we can use that to help understand how the universe is expanding. And the expansion of the universe is related to what's in the universe. That's kind of intuitive. And so it turns out that the universe is expanding in a way that requires it to be flat. And given other observations and given other constraints, we see that there's not enough matter and there's not enough radiation. So there has to be something else. And it works out that that something else is most likely this cosmological constant, which you'll commonly hear called just lambda, like that triangular Greek letter lambda. I hope that answers the question. I get really excited about the cosmological constants. I got a little distracted there.
And this next question kind of relates to the previous question. So it's from Roger, and he asks, will the expansion of the universe cease and a big crunch occur, and a new Big Bang happen? And this is a really cool question because this was a pretty popular, I don't know how popular exactly, hypothesis in the past when we didn't have so much evidence for dark energy. But since dark energy causes the expansion of the universe to actually accelerate, it's always expanding faster than it was the minute before. It seems unlikely that a big crunch, meaning that the universe would collapse back in on itself, would happen since it's only going faster. There's no evidence of it slowing down and definitely no evidence of it crunching back together. Of course, that could happen. We have no idea what might happen in the future. Maybe some weird new physics or strange event will turn off dark energy, so to speak. But at least in my opinion, it seems very unlikely. All right, I think we are going to put a pause on questions and move on to a quick demonstration that Maxwell has. This is one of the most common demonstrations, I would say, on this topic. So those of us who study astronomy in school see it time and time again, but it's something that's really good to see at least once, because a lot of people kind of assume that you have seen it when they talk about how this stuff works. So it's a good thing to have in your head to be able to visualize. So I'll pass it off to Maxwell.
All right. I like to call it the balloon of insignificance, because you can kind of take the meaning philosophically, whatever you really care for it to mean. But really what we're trying to demonstrate here is the idea of, are we the center of the universe? I mean, there has to be a center somewhere, right? And another idea is a very important distinction, which is between the universe is expanding. That does not mean everything is physically moving away from each other. It just means it's all getting further apart. So in my hands here, and hopefully you can see relatively well, I know my camera's not extraordinarily high quality, is a balloon, a simple balloon. It's a white balloon with blue dots. Our blue dots are wonderful little galaxies, which is kind of fitting, because blue galaxies well, they're at least not red, so they're at least possibly producing stars. So we're a little earlier on in the universe. You can tell it's an astro joke in the fact that barely any of us laughed. So imagine this is your universe. It's a fun little ball. You start out much, much smaller. We start out in the Big Bang here. And here we have all our wonderful little galaxies. Now, I want you to ignore the fact that since my galaxies are on a piece of rubber, they are themselves expanding. Let's pretend, use our fun imaginations, that they are staying the same size. Well, as I expand my universe, which I'm just going to... the points get further and further apart from each other. And as we contract, if we do have a big crunch, they get closer and closer together. Now, there's a key distinction there. Would you say that my points are physically moving away from each other, or would you say the balloon is getting bigger? Now, the more appropriate thing to say isn't that my points have all of a sudden gained sentience or left the rubber itself and just flown away. No, the points themselves stayed on the rubber where they were, but the rubber expanded. Now, the rubber is our universe. Our universe expands like a grid, but we are on the points of the grid. So yes, we move further apart, and thus the distance gets bigger. I have a lot of balloons. So like the distance on our dots, they get further and further apart from each other, but they themselves are not moving. It is the balloon that is growing larger. This may seem silly and this may seem nonsensical, but it's a very important distinction, because it helps suggest that the Big Bang didn't just fling a bunch of stuff outwards and there you go, that's the universe. No, it helps us suggest that the Big Bang helped create reality itself, helped make space and expand it. And so that's the demonstration that I'm calling the balloon of insignificance, because it at least shows you that no, you are not the center of the universe. In fact, every single point could be the center of the universe. So you can view it, either side of the same coin. But that's what we have for you today. And unless there's any new pressing questions, I believe that that's all we have planned for you all today.
Yeah, I think that's it. So I hope everybody enjoyed the demonstration and the talks, and this is the last Universe at Home event for this semester. So look out for information about next semester, and we hope to see you then. All right, bye.
Bye, everyone.